Welcome to the channel Quest Edu Physics students. It is your YouTube channel. If you like this channel, subscribe it and please forward the same to your friend students. Here in this class, we are going to learn about the construction and working of a simple microscope, students. What is a simple microscope? The simple answer is it's a magnifying glass. It's a magnifying glass. We use a converging lens. The convex lens as the magnifying glass, and it is the simple microscope. First of all, we have to understand few terms which are related to the simple microscope, students. That means which shows a major part in the derivation of the formula for the magnification. That is least distance of distinct vision and also angle of vision, students. First of all, we have to understand what is the least distance of distinct vision. It's quite simple, students. It is the minimum distance from the eye where we can see the objects clearly. It is the minimum distance from the eye where the object can be seen clearly. For a healthy eye, the least distance of distinct vision is 25 centimeters, students. For a healthy eye, it is 25 centimeter. Often it is shown with the letter capital D, students. Don't mistake it as a diopter. Okay, it is shown with the letter capital D. And the second is angle of vision. It plays a major role, students. It is the angle made by the human eye with the object, students. Generally, this visual angle for the normal eye is 60 degree. The magnifying power of a lens, always depends upon the visual angle only. Okay, students. If we increase the visual angle, automatically the magnifying power also increases. It is the basic principle of simple microscope. The principle is increasing the visual angle, resulting into magnifying power. Okay, students. Let's go with the convex lens, which has smaller focal length. And I already told you, if you keep any object in front of your eyes at a distance of 25 centimeter, you can see it clearly. It is the least distance of distinct vision. Let's go with the construction and working. Actually, we have to take a biconvex lens of shorter focal length, students. Let's say it is the biconvex lens of shorter focal length. Okay, here I am locating its optic center. Optic center means what, students? We are making a light ray to pass through the optic center, joining the two radius of curvature, students. This is the first radius of curvature and it is the second radius of curvature. Here you know that a lens always have a focal point and the focal length. And what is the focus? It is the focal point or the principal focus. It is the point where the rays will meet after refraction. Here we are taking an extended object, students. It is the extended object. What is an extended object? Which has measurable dimensions. Let's say it's the extended object. We named it as A, B. Okay, students. And we kept this extended object in between the optic center and as well as the principal focus of this biconvex lens. Here we have to remember what the methods of image tracing. As we have learned that to trace the image, we need at least two light rays which are coming from the object. Here we are taking the two light rays, students. One is parallel to the principal axis, it is, and the second one which is passing through the optic center, students. This ray which is passing through the optic center doesn't get deviate. You know this, students. Then it gets refracted and it passes. Here if you observe this one, the gap has been increasing all the time in between these two rays. Okay students, here actually we kept our eye very close to this lens. Almost it is in contact with the eye. Okay students, it is very close. Your eye is very close here. Okay students, if was these two, they can't meet at a particular point in this way. That's why we are producing them back. Okay, I am producing it backward and also I produce it back. The two will meet at a particular point where we will get image. Okay students, it is the image. We are naming it as A dash, B dash. It is the virtual image students. It is the virtual image. Now see what we did. We took an object. Okay, the object is kept. What is that in between? Optic center and as well as focus. Let's say the distance of the object is u. Okay students. And what we did, we formed the image at least distance of distinct vision. It is the D students. And what is the visual angle? It is the angle made by. Okay, the image with the eye students. It is, I am naming it as beta. It is a mechanism what we did. Actually the eye is very close to us. Here we have to learn one term which goes with the magnification students, or magnifying power. Magnifying power of a lens can be defined like this students. It is the ratio of angle subtended by the image. Is the ratio of angle subtended by image to the angle subtended by the object when the object is kept at least distance of distinct vision students. Okay students, here we can define it like this. It is the ratio of angle subtended by the image to the angle subtended by the object when it is kept at least distance of distinct vision. Here clearly you are getting here the angle subtended by this image with the eye here. Eye is very close to this. Is the beta, but we don't know where is the other angle. Yes, students, I am producing it. Okay, here if it is AB, automatically it is also AB students. It is A and it is AB dash. Getting me? Then we have to take the angle students. Visual angle made by the object. It is alpha. Okay, what I said, it is the visual angle or angle subtended by the object when it is kept at least distance of distinct vision. First we see the object without this lens. Here eye is very close here. Then after we kept the lens in front of eye and we adjusted the distance of the object up to B. I hope you understood. What is the magnifying power here? It is the angle subtended by image to the angle subtended by object at least distance of distinct vision. Here these angles I am noting. Beta is the angle subtended by image. Okay, don't get confused over here. OAB, it is the image. Beta is the angle which is related to that, but I am showing that this one. Here I am taking. Here the angle remains same. Okay students, then we can write it as beta by alpha. But from this geometry, I am taking the beta and alpha value students. I am taking the triangle. From triangle, OAB. Okay, tan beta is equal to, opposite is, it is AB by U students. I am not putting any sign convention here. Similarly, we have to go with the tan alpha, OAB dash. From triangle OAB dash, tan alpha is equal to AB. Okay, this AB is equal to AB dash. AB by, it is D. Here also I am not taking any sign convention. We had the alpha and beta and putting here, since they are very small, beta can be replaced with tan beta and alpha can be replaced with the tan alpha students. Then it can be written as tan beta upon tan alpha, and finally we got AB by U divided by AB by D. AB we get cancelled and we get D by U. It is the formula for the magnification, students. Here the magnification is the ratio of the image distance to object distance. If you keep the sign convention also, you will get the same results. D has to be taken as negative and U also is negative. Then minus minus get cancelled and you get the magnification as D by U. Since it's a ratio, it doesn't have any units, you know that, students. Now we are drawing, or we are getting the formula for the magnification in terms of a focal length of the lens. Let's say the focal length is F, and you know that from lens formula or lens equation, the focal length, image distance and object distance are related like this. 1 by F is equal to 1 by V minus 1 by U. It is for lens, students. Here I am multiplying both sides with the D, students. D by F is equal to D by V minus D by U. Here V is what? V is the image distance, students. It is the image distance. Here image is formed here. Okay, and it can be written as D by D minus, I am using the sign convention here, it's a minus. It is minus of D by U, means what? Plus D by U. Here it is D by F. Here D get cancels and we get D by F is equal to minus 1 plus D by U, or 1 plus D by F is equal to D by U. Already we know that D by U is equal to magnifying power. Then M can be written as 1 plus D by F. These are the two formulas which can be used to find the magnification, students. That is magnification in terms of focal length, magnification in terms of least distance and object distance. Here if you see this, object distance is utilized here, object distances disappear. And what is meant by this? Here this formula is for the magnification in case of the strained eye, students. If you form the image under these conditions, your eyes get strained. Okay, students. Eye gets strained means what? You cannot watch the image for longer time, though it has more brightness and its intensity is more. Brightness means intensity. Okay, to see the image for the longer time, we have to form the image at infinity. Okay, students, what we have to do? The same we have to do to get the image at infinity. The same lens, eye is very close to this one. This time we are keeping the object at focus itself. Then we have to do the regular things. One ray has to pass like this. After refraction, it passes through the focus. Because these two rays, they appear to be parallel to each other. It is the object distance is equal to focal length here, students. If I extend them back, they meet at infinity. That means what? V is infinity. Okay, students, then we are using the same relation. 1 by F is equal to 1 by V minus 1 by U. I am putting the V as infinity here. 1 by infinity is equal to plus 1 by U. Okay, students. Then multiplying both sides with the d, what I get? D by f is equal to 1 by infinity is 0. It is d by u. Here you know that d by u is equal to, again it is a magnification. M is equal to, it is d by f. It is the equation to get the magnification at infinity. Here in this case, maybe the image is not sharp and not magnified as compared to the image which is formed at least distance of distinct vision. Though it lost its intensity, but you can watch this image for a longer time, students. Okay, these are the equations which are related to simple microscope, students. I hope you followed the class. Thank you for watching my channel. Students, in this class, we are going to learn about the compound microscope. Okay, students, welcome to Class 10 Physics. If you like this channel, please promote this channel by sending the link to your friends, students. Here, we are going to learn about the compound microscope. In previous classes, in previous lectures, maybe you learn about what is a simple microscope is and why another system of lenses is developed instead of using the simple microscope. Briefly, I will explain, students. Here, all these instruments are used to increase the view of the field and as well as the size of the image. Okay, I mean to get the magnification. If you use a simple microscope to observe the magnification, definitely it gives you some magnification, but it has some aberrations. Maybe the image is not clear, or it is, what's that, extra color. Such things we call as the spherical aberration and as well as the chromatic aberration. Here, chroma means color, students. Spherical means what? The image appears to be blurred. To come out such kind of defects, a new system is introduced, system of lenses. It is known as the compound microscope. Compound microscope has two lenses, students. One lens is set as the objective, which is towards the object, and second one is set as the eye lens, which is near to the eye. In books, sometimes they say it has the eyepiece. Maybe. But better, eyepiece has another meaning, students. In coming lectures, we will understand what is the difference between the eye lens and as well as the eyepiece. These two lenses, one is the objective and second is the eye lens, are mounted coaxially in a metal tube, students. They kept coaxially in a metal tube, and the distance between the two lenses can be adjusted by using an arrangement known as the rack and pinion. The arrangement is known as the rack and pinion. And you are aware of that, students. Most of you know about the binoculars. If you observe a binocular, at the center you will get a screw-like structure which can be rotated, a wheel. With that you can adjust the distance between the lenses with your eye in case of a binocular. The same thing is arranged in this compound microscope and we call it as the rack and pinion. It is indirectly telling us that the distance between the lenses can be adjusted by using the rack and pinion. That means what? By adjusting the distance between the lenses, we have the availability to, get the image at various positions, students. By using a compound microscope, okay, generally we have the two different positions to get the images. Okay, students. One is at least distance of distinct vision and second is at infinity. Here the question arises, why we select two, why we have the two positions to get the image. You know about this, students. If the image is found at least distance of distinct vision, it has more intensity. I mean, it has more brightness. Maybe it strains your eye. By making the image at infinity, the eye gets less strained. You can continuously see the image for a longer time sequence. That's why we derive the two expressions for the magnification. One is when the object is the image is formed at infinity, and second is the image is formed at least distance of distribution. Maybe most of you know how this compound microscope looks. Generally, these kind of arrangements we see in medical laboratories. If you watch this diagram, you will understand how it looks. And see, maybe you saw somewhere that means in lab this kind of structure. Students, and we keep a plate. If you go for what is that medical test, taking the blood samples and other, the technician there uses this kind of instrument. Maybe you understood what is the compound microscope is. By using this, we can get a larger magnification, students. Okay, students, let's see how it looks. Already I told you it consists of two convex lenses of different focal lengths. Okay, students. Here it is the first lens. Know that it is a double convex lens. Okay. The second one is also a double convex lens, students. Okay, these are the two lenses, students. This one is known as the objective lens. Okay, it has a focal length of f, and it is objective. That's why I'm writing it as the f4. And see the second, students. And generally, it is kept at the eye, we call as eyelets. And I said these two are mounted coaxial. That means what? They have the common axis. They have the common axis. Let's say it is the optic center of the first lens, and we have the optic center of the second. If you join the two lines, simply we can say it is the principal axis of the both. The principal axis of the both lenses. Okay, students. Thereafter, we have to trace the diagram, students. What we have to do, we have to take an extended object. Before that, we have to locate the focus and other things. Say it is the focus of the first lens. I'm calling it as therefore. Immediately we will get a more focus here. In the same way, if you say it is the eye lens, it has its focus. We are calling it as the FE. Students. Here, then after, what we have to do, we have to take an extended object. It is the object which is taken. I'm calling it as the extended one. Means it has the measurable dimensions, students. And you know that how to trace the ray diagram. The simple technique is you have to take the two rays at least to trace the image. One has to pass parallel to the principal axis. Okay, students. The other should pass through the optic center of the lens. Here. If you produce them back, after refraction, they meet at a particular point, there we will get the image. Okay, students. It is the image. What I get. Okay, students. For convenience, I'm extending the length of the lens. Actually, it doesn't require. Even though to make the diagram easy and somewhat good. Okay, I'm taking few liberties. Results. The image is formed here. Here it is the object, call it as A, and it is B. And we will get an image here. You know that the image is formed beyond the focus length, focus of the objective. Okay, students, call it as A dash, B dash. Okay, students, A dash and B dash. Here, now I am taking the focal length of this second lens. Instead, this lens has a focal length of FE, or you can say this lens is LE, and automatically it is yellow. Okay, students. See this, it is the image. Now, by using the rapid beam, I am adjusting the position of this image. Now, I am taking this image, what's that, in between the optic center and as well as the focal length of the eye lens. In between optic center and as well as the focal length of the eye lens. Okay, this image is formed between the optic center and as well as the focus. Now we have to go with the final diagram. Here you know that the image tracing method, one ray has to be taken parallel to the principal axis, travel along, and the second has to move through the optic center students. Yeah, like this. Okay, it is moving on. If we extended ray, this ray backwards, we can extend it like this. In the same way, after diffraction, it might passes like this. These are the rays. If you watch these two rays, you will find that the gap between the two is increasing. So they can't meet at a particular position here. Then we have to produce them back. Producing it backwards. And these two will meet at a particular point, and we'll get an image here. It is A dash and it is B dash. I'm calling it as A double dash and B double dash. This is. It is a diagram what is required to know about the magnification of a what's that compound microscope. It is the compound microscope. I hope you understood how to draw the diagram and what is the terms related to these. These students, if you watch it carefully, you will find that for the first lens, this is the object distance. I am calling it as O. And similarly, we found the image here. It is the image distance. I am calling it as MO. Okay, students. Here we made the image to form at least distance of distribution. Okay, and we know that it is said as the T. Okay, students. Here we have to get the magnification. The magnification is due to the two lenses, students. That's why we are taking the magnifying power is the multiplication of magnification produced by objective and as well as magnification produced by the eyes. Welcome back to Quest Edu Physics students. In this class, we are going to learn about the magnifying power of the compound microscope. In early video, we learnt about the construction and working of the compound microscope. In this video, we are finding the magnifying power. Here, first we have to understand what is the magnifying power is. As a lender, it is a ratio of angle made by the islands to the angle made by the objective when the image is formed at least distance of distinction. This is the magnifying power. It is the definition of the magnifying power for a compound microscope square. Roughly we can say magnifying power is nothing but the product of magnification produced by the objective and islands. Let's go with the problem student, derivation students. So this it is the objective lens and we are locating the optic center here and calling it as the O1 and it is the principal axis students. Okay students. And it is the focal length of this objective and I am taking an object that it is an extended object students. It is AB and name it as. You know the method of image tracing. One ray has to pass parallel to the principal axis. Here it is the ray which is passing parallel and one has to pass through the optic center. It is. After refraction, they meet at a particular point, they will get the image. Let's say it is the image which is formed. Here, I'm naming it as A1, B1 students. Okay. And here, it is the object distance, UO, and it is the image distance for the objective. While constructing this, you have learned that the two lenses are mounted coaxially in a metal tube. Okay, the distance between the lenses can be adjusted by using the rack and pinion I said. Here we have to take the common axis. It is the common axis. I am taking one more ray, one more lens. Let's say it is the eye lens. Okay, students. Okay. Now say this image A1, B1 is taken as the objective by the eye lens. Okay, one has to pass like this and one has to pass through the focus students. If you extend these rays, see the gap being increasing. This is the focus of the items. If you produce them back, they meet at a particular point, there we'll get an image here. Say this image as A2, B2. Okay, what did happen here? This one, A1, B1, acted like the object for the second lens. And this object is taken as the object by the eye lens and it forms the image here. Okay, let's do some little geometry students. I'm taking a ray which is parallel to the head of the object and it might pass like this. Okay, students. Let's say it is the angle subtended by the image, this one. Say it is O2. Okay. With A to B2 is beta. And similarly, I'm taking a point from B2 and it is parallel to this. If it is AB, it might be equal to AB. It is AB students. Then this AB is making an angle of alpha. Okay, students. As you have learned that magnifying power of a compound microscope is the angles subtended by the image and as well as the object with the lens, where the image is found at least distance of distinction. It means what? This distance is least distinction. That means it is the image distance formed by the eyelets. Or simply you can write here VE is equal to D. Okay, and this one is what? UE, distance of the object from the eyelets. Okay, students, here see this. This one, this image which is formed by the objective acts like the object for the eyelets, and it takes this as the object and forms the image at least distance of distinction. Okay, students, we watch this carefully according to the definition. Magnifying power M is equal to what is said? Angle subtended by what? Image to the object, that is beta by alpha. And they might be equal to tan beta by tan alpha. Why I am taking tan beta and tan alpha here? If you watch it carefully, if you take the triangle here, O2BA is a triangle, and similarly O2B2A2 is one more triangle. Okay, students, here these are very close to each other. Okay, that's why I am saying that it is near to tan alpha and tan beta. Let's take the value of the tan alpha from the triangle O2AB and O2AB. That is tan alpha is opposite by adjacent. That is AB by adjacent O2B. O2B. Or simply you can say O2B2, because B is coinciding with the B2. And also tan beta. Here this one, this value. This one, O2, A2, B2. Okay, is equal to what we have? A2, B2 by O2, B2. Okay, students, I hope you understood. From the triangle O2AB, we took the value of the tan alpha, and similarly from the triangle O2, B2, A2, we got the tan beta as A2, B2 by O2, B2. According to the definition, magnifying power is equal to beta by alpha, and substitute in the value set. I got the magnifying power M is equal to A2, B2 divided by O2, B2 by AB by O2, B2. Here O2, O2 get cancelled, and I got it as A2, B2 by AB. It is the magnifying power of the objective. Magnifying power of the objective, students. What I said is the product of the magnifying powers of eyelets and as well as the objective. Okay, students, see this. I can rewrite this equation. M is equal to A2, B2 by AB as A1 by B1 by A1 B1. I'm just multiplying and dividing with A1 B1. What is A1 B1? A1 B1 is the what's that? Image. Okay, height of the image formed by the objective lens. Okay, students. Then it can also be written as A2 B2 by A1 B1 into A1 B1 by AB. Now see this. Here what is A1 B1 by AB? A1 B1 is the image. AB is the object. As you know that, okay, it is the magnification. What is the magnification? height of the image by height of the object. Okay, it is a magnification produced by the objective, and it is a magnification produced by lines. Here you have learned that. Here it can be A1 B1 by AB. Is the magnification of objective, and it is A2 B2, A2 B2 by A1 B1 is the object. Magnification of the objects. M is equal to MO into M. Okay, students. Okay, and also students, you know that magnification produced by objective MO is equal to image distance by object distance. VO by UO. VO by UO. I'm taking the sign convention here. UO has to be taken as negative since it is in front of the lens. And similarly, it is a simple microscope, students. For simple microscope, the magnification ME is equal to 1 plus D by FE. Okay, students. That the total magnification M is equal to V naught by U naught into 1 plus D by FE. FE is the focal length of the eye lens, or it can be written as M is equal to, okay, V naught by magnitude of the U naught into 1 plus D by FE, students. Is the formula for the magnification. Okay, students, then see, we are going further. Imagine that this object is coinciding with FO. Means U naught can be taken as FO. Okay, and say this image which is formed here is very near to the eye, it's just back. And the distance between the two lenses is L. Okay, the gap is very small. FO plus FE is equal to L. And if you substitute this value in this relation, you will get M is equal to VO by FE into 1 plus D by FE, students. Okay, there is one more formula. Now say, students, here this image, this one, actually I showed in the diagram, it is somewhat bigger and far away from the lens. In actual practice, this image will be formed near to this. Okay, students, then we can consider VO as L, students. Then this equation can also be written as M is equal to L by FE into 1 plus D by FE. Okay. Here, if it is the image is formed at infinity, then you can rewrite this formula M is equal to LD by FO. Okay, it is FO, students. I wrote here FO into FE. It is one more development, students. I hope you understood how to derive an expression for the magnifying power of the compound microscope. Let's have a nice time. Please subscribe my channel and forward the same to your friends.